One. Evaluate. These you should be able to do pretty quickly. Natural log of 1, everybody. What is it? It's 0, right? It's 0. Uh, and then log base what? What base is that? I didn't write a base. Oops. What base? Oh, it's base 10. That's the common log. Yeah. And it's 1 over a million. 1 over a million. What does that equal to? -6, right? Log base 10 is easy when you have powers of 10. You just count the zeros. Because it's in the denominator, we got to flip it. So anyway, log of 1 over a million is -6 because 10 to the -6 is 1 over a million. Okay, and the natural log of 1 is 0 because e to the 0 is 1. Remember that? All right. Your calculator can handle two bases. Your calculator handles base e and base 10 directly. There's a button on the left-hand side of your calculator called LN, and there's a button right below it called LOG. So it's pre-programmed to handle base E and base 10. But what if we want to evaluate things that have different bases? Okay, so you'll need a calculator for this little activity, and you could do exactly what I'm going to do right here. If you don't want to stand up, you could go ahead and go to your Canvas course and go to the TI standalone calculator. Some of y'all like standing up. Uh-oh. Oh, it took me to the wrong screen. That's not the screen I want to go to. I can't do anything from that screen. There we go. Patrick.
How's it going?
It's going well. We started without you. There you go. All right, so there's my calculator. You can do the same thing. There's a way to change the base, and here's what's called the change of base formula. Change of base formula. It allows you to take a log that is in any base prescribed B. We'll call that, oops, that's not what I wanted to highlight. Just that. Nope, I did it again. Why is it doing that? There you go. So if you have a log base B, B could be any number that's legal. It's between 0 and 1, that's logarithmic decay. Anything greater than 1, that's logarithmic growth. You could change it to any other desired base that you want. Okay? You could change it to base E. If you wanted to change base B to base E, which would be the natural base, it would be the natural log of the argument, x, over the natural log of the old base. Okay? Let's say you wanted to change base B to your common base, base 10. Then it would be log of the argument, x, over the log of the old base. Let's say you wanted to change it to base 7, right? Then it would be log base 7 of the old argument over log base 7 of the old base. So in general, your new base that you can choose, your new base could be base A. And all you have to do to change your old base B to your new desired base A is take the log of base A of your old argument over the log base A of your old base, okay? So that's pretty easy to remember which one goes in the numerator, because if you notice the way this is written right here, it's kind of like x over b, isn't it? The x is kind of elevated because the b is the subscript, so the base goes in the bottom. Now, what we're primarily going to be interested in is putting them in terms of base E normally, but we could choose any base that we want. So for instance, if I want to evaluate log base 0.5 of 14, let's think about what an answer to this might be before we start. We're asking ourselves 1/2, that's 0.5, right, to some power x equals 14. If I want to let this equal x, x is the exponent. 1/2 to some power of x equals 14. What do we know about x? Is there going to be 1? 1/2 to the first is a half. That's too small. What about 2? 1/2 squared. That makes it 1/4, right? That makes it smaller. We don't want that. I need to make x negative, don't I? To make x negative, it's going to flip it. Now I can look at powers of 2. So let's think about it. 1/2 to the negative first. That would be negative 2 to the negative first. That'd be 2. That's too small, right? What about to the negative second? That would be 2 squared, which is 4. That's still too small. What about negative 3? That'd be 2 to the third, which would be 8. Is that still too small? What about 2 to the negative fourth? That would be 16. That's too big, right? So it's going to be somewhere between -3 and -4. So I'm going to say -4 is less than x is less than -3. Just by kind of playing around with it in our head. I know that x has to be somewhere between -4 and -3. So I know log base 0.5 of 14 is some number between -3 and -4. Let's see if we can figure out exactly what it is. To do this on the calculator, we're going to need to do the change of base formula. So we're going to say that this is equal to the natural log of 14 over the natural log of 0.5. Okay? We could choose any base, but I prefer to use the natural base. Okay? We write it out on our paper first, and then we type it into the calculator. On our quiz, I'm going to want to see this. Okay? This is going to get a check right here. And now for the answer, we go to the calculator. Alpha x gives you your horizontal division bar, and you can hit ln of 14, close parenthesis, divided by ln of 0.5, close parenthesis. And if you hit enter, you get -3.807. We go to 3 decimal places, remember. Is that between -3 and -4? It sure is, yeah. Yeah. So we were able to pin it between two integers just by thinking. And that's the whole purpose of this class, is to think. So that's good. Now, you got an error. No, that's the only rule. The purpose is to think. The only rule is to care. Now, what if I wanted to choose base 10? I could have said that this is also log of 14 over log of 0.5. Let's see if that gives us the same answer. Go to alpha x and now hit the log button, which is right above ln of 14, close parentheses, divided by log of 0.5. Okay? If it's a different number than -3.807, then we'll quit studying logs for the rest of the year. We'll just watch Charlie Brown's Happy New Year special. Okay? Does that sound good? Ah, it's the same answer. Thank goodness. Thank goodness math works, right? So, does it matter if you use base E or base 10? No, your calculator is pre-programmed for both of those. You could actually, if your calculator is programmed for base 25, you could use base 25. But we prefer to use the natural log in this class. So if you have no preference, try to develop a taste for the natural base. It's all natural, so it's healthier, right? Okay, let's do the next one. Log base 6 of pi. So here's what we're thinking to ourselves. This is equal to something. So I know that 6 to some power of x equals pi. Let's think about where x is going to live. Let's try 6 to the 0. 6 to the 0 power is what? 1. That's too small, right? Because pi is what? 3.14. So it can't be 0. It's going to be bigger than 0, right? What about 6 to the first? That's 6. That's too big, right? So we know x already has to be between which two numbers? 0 and 1. We know that, yeah, it's got to be 6 to some power between 0 and 1. Maybe it's a half. Maybe it's the square root of 6. Who knows, right? So here's what we're going to do. We're going to go ahead and say that this is equal to the natural. You could say x equals. If you say x equals at the top, you could bring x equals down at the bottom, but you don't need to put x equals because it was an expression to begin with. But it's the natural log of pi over the natural log of 6. Does it matter which one's in the top, the pi or the 6? Does it matter?
Yeah.
Oh, it does. It does. The pi has to be in the top, and the 6, which is the subscript, has to be in the bottom. All right, now I can type. It doesn't matter if I use base 10 or base E, Ryan, but it doesn't matter which one's in the top or the bottom. So I get the natural log of pi, which we use the pi button, which is second caret, all over the natural log of 6. And we get 0.638, 3 decimal places. There it is. And that's between 0 and 1. I could really give you these questions then on a test as a multiple choice question without a calculator, couldn't I? As long as your answer choices were inequalities, right? As long as this was an answer choice between 0 and 1, you should be able to figure that out without a calculator. All right, let's try this one. Log base 3.6. Can we have bases that are decimals? Apparently so, yeah. As long as they're between 0 and 1, like for exponential, that's decay, or bigger than 1, that's growth. So we're telling ourselves 3.6 to some power x, which is the log, is equal to 17. Well, 3.6 to the first is 3.6. That's too small, right? 3.6 squared,
That's too small.
that's going to be too small still because 3.6 is like 4, and 4 squared is 16, which is too small. So it's going to be bigger than 2. What about 3? That might be too big, right? So I'm thinking it's between 2 and 3. I'm thinking that this is between 2 and 3. Well, let's go ahead and write it out. It's the natural log of 17 over the natural log of 3.6, and we'll type it into the calculator, alpha x again, the natural log of 17 over the natural log of 3.6. Big bucks, no whammies, and we get 2.211. Again, I truncate. If you want to round, because you're used to rounding, that's fine. Just make sure you go to 3 decimal places. So pretty handy, right? Pretty handy, this change of base formula. So you can evaluate logs now in your calculator of any base that you want using the change of base formula. All right, here's another application of the change of base formula. Let's say we have an expression something like this. This makes a great, fantastic multiple choice question on a test. This one right here. Fantastic multiple choice question, MCQ. These appear to make good MCQs as well. I want to evaluate that. Okay. I have 1, 2, 3. I have 4 different logs. They're all being multiplied together, so they're factors, and they're based 3, 2, 7, and 5. Now, I could go ahead and just start typing this into the calculator, but my calculator can't handle base 3, 2, 7, and 5 directly. So you always need to make sure you're writing on your paper first what it is you're putting into your calculator. So what I'm going to do is I'm going to go ahead, instead of having 4 different bases, I'm going to put it all in terms of one base. And which base do we choose in here? No, that's in your science class. We choose 10. And here we choose base E. We choose base E. Right? We're going to use the natural log. It's one fewer letter. So when you're writing out ln of a number instead of log, it's more economical as well, right? You don't have to write a whole letter. So I'm going to say it's the natural log of 5 over the natural log of 3. That's the first one. And instead of using parentheses, I think I'm just going to put a dot to represent the multiplication. And then log base 2 of 7, that's the natural log of 7 over the natural log of 2 times the natural log of 3 over the natural log of 7 times the natural log of 11 over the natural log of 5. And now, of course, someone who is caring, but maybe perhaps not thinking, will go straight to the calculator now and start typing in these 8 factors, okay? But the person who's thinking is always looking to simplify early and often. Since I have a bunch of factors that are being multiplied together and now I have denominators, we know that things divide out that are the same to give us 1, don't we? Do we have any factors that are the same in the top and bottom? Yes, the natural log of 5s divide out over here. They don't have to be right next to each other to divide out, do they? The associative property of multiplication allows us to associate them. Anything else dividing out? The natural log of 7s divide out, and the natural log of 3s. I see the natural log of 3s divide out. So this is really just the natural log of 11 over the natural log of 2, which now I could type this into my calculator if I was interested in a decimal. But what if this is a non-calculator multiple choice question? Ruh-roh, non-calculator. Let's see if I can rewrite this in a different format so that I can figure out where this thing lives between which 2 integers. The change of base formula not only works from left to right, believe it or not, it also works from right to left. So can I condense this down to the log of a single base? I can. What would it be? It would be log base what? 2 of what? 11. And now I can think off to the side here on my workbench, 2 to what power is 11? X has to be between which 2 numbers? 3 and 4. Yeah. Now, if this were a non-calculator question on the test, I can have the inequality as an answer choice, have you pin it between 2 integers, or I can have this as an answer choice. Either one of those are good answer choices. Now, for kicks and grins, just because we have our calculator, let's go ahead and see what it's equal to. It's the natural log of 11 over the natural log of 2. Yeah, which of course, for what it's worth, it's 3.459. So you see how the change of base formula gives you the opportunity to put everything on the level playing field. You have multiple bases. Let's put them all in terms of one base, and then we can compare apples to apples. But we're thinking the whole time, aren't we? We're thinking the whole time. All right, sweet. That's a good little application. Okay, shifting gears here a little bit now. We're going to look at solving logarithmic equations. We've already seen logarithmic equations way back up here on example 1, but those were boring equations because they were already solved for x. All we had to do is simplify and evaluate the other side. There are other equations that involve logs that are more interesting, have the variables that are not already solved for. Okay? So that's what we're going to do on example 6. It says to solve the following equations for z. All right, so we read this one. We know it's an equation. We see the equal sign. We know it's a log equation because we see the log. Everyone see the log? What's the base there? 10, okay? I know we don't need to write the base 10, but when you're solving log equations, it's kind of nice to see the base. So that would actually be the first thing I would do. I would write the base 10. So how can we go about solving this? Log base 10 of some number is 3. What's another way to interpret that sentence? Instead of saying log base 10 of z equals 3. 10 to the third equals z, right? That's how we interpret logs. 10 to some power equals z. That's how we interpret logs. 10 to some power, in this case 10 to the third power is equal to z. Oh my gosh. Just converting that to exponential form gives us the solving for z part, and we get z equals what? What's 10 to the third? 1,000. Wow. Now that's one way to do it. That's doing it by thinking about what it means to be a log. The other way to do it, here's the other way to do it. This is the algebraic way. And we're going to exponentiate both sides. Exponentiate both sides. I showed you this yesterday. It's a little bit more involved, but it works. So you're gonna take your log base 10 of z equals 3, and what you do is you take the base 10 and you put it now as the base of both sides. Whatever you do to one side, you could do to the other side, including exponentiate. So now the two sides are exponents. See what I did there? The two sides are now both exponents on the base 10. And of course, what happens on the left-hand side? What's 10 to the log base 10 of z? It's just z. And that works because how are 10 to the x and log base 10 of x related? They're inverses of each other. Very good. That's the main property here that we want to make sure we're emphasizing. 10 to the log base 10 of z equals z. They're inverses, so they undo each other. All right, and then I get z equals 10 to the third, which of course is z equals 1,000. Do I care which way you do it? No. Right now, the equations are simple enough. You could just solve it by thinking in terms of doing the around the world thing, essentially, what I said. 10 to what power? 10 to the third power is z. All right, let's try this one here. This one, not quite as straightforward, right? But it's log base 2 of z plus 1. So my unknown is part of the argument, z plus 1. Let's go ahead and do this one the algebraic way. I want you to kind of get in the habit of doing that because as these get more and more complicated, they become less and less intuitive, okay? So what I'm trying to do here is I'm trying to peel back the layers just like I would in any algebraic equation to get it to z. Right now, standing in front of the parentheses, which is my obstacle, is log base 2. How do I undo logging something base 2? Yeah, and what do we call that? What's the? We exponentiate both sides. Okay, that's the algebraic technique. How do I unlog something base 2? I exponentiate it base 2. And I'll let you get away with doing it like this if you want. Okay? You could just add the 2 to the bottom left. So now the left side is an exponent and the right side is an exponent. Everyone okay with that? I'm okay with that too if you do it like that. Now, what happens on the left side? What's 2 to the log base 2 of blob? No, 2 to the log base 2 of the blob, whatever the blob is just equal to the blob. I use the word blob to represent anything, in this case z plus 1, right? 2 to the log base 2 of blob is just the blob. In this case, the blob is z plus 1, and I get 2 to the 4th, which is what? What's 2 to the 4th? 16, and now we're back in algebra 1, right? You subtract 1 from both sides, and you get z equals what? 15. There you go. It's fun. It's easy. It's easy. All right, do this one on your own. Go. Don't be afraid of fractions. Fractions are numbers too. All right, let's see how you did here. We got a log equation. The unknown z is in the argument. I need to get at the z, which means I eventually need to get at the 2z plus 3. The 2z plus 3 right now is being trapped inside of the log, which is out front. So that's my first obstacle, right? So how do I unlog something base 1/2? What's the term? I exponentiate both sides base 1/2. And I can show that by doing this. I will allow you to show that by just adding a 1/2 to the bottom left. Now on the left side, 1/2 to the log base 1/2 of blob is the blob, which is 2z plus 3. And over here I get 1/2 to the 5th, which is 1 over 2 to the 5th, which is 1 over 32. 1/2 times a half times a half times a half times a half is 1 over 32. Now, from here, you can either A, embrace the fraction, or you can multiply both sides by 32 and get bigger numbers. But we're going to embrace the fraction here. Let's just subtract 3 from both sides. So I get 2z equals 1 over 32 minus 3. Now, off to the side, I got to think what that is. What's the common denominator? 32. What's 32 times 3? 96. So that's really negative 96 30 seconds, which is negative 95 30 seconds. Okay, so this is my workbench right here, my workbench. So I got 2z equals negative 95 30 seconds. And now all I got to do to solve for z is divide both sides by 2. But since there's a fraction on the other side, I'm just going to multiply both sides by 1/2. So I get negative 95 30 seconds times 1/2, right? Dividing by 2 is the same as multiplying by 1/2. And what I would do first is look to see if I can divide out. Is 95 divisible by 2? No. If it were 96, I would divide out those two instead of just multiplying straight across. You always look to go small before you go big. But in this case, I just multiply straight across and I get negative 95 64ths. And there it is. We have a systematic process now for solving log equations when the variable is in the argument, don't we? It's like a new technique, right? It's real easy for us to say when it's 2z equals something, how do I solve for z? We divide both sides by 2. That's instinctive. You learn that in Algebra 1, that to undo multiplication, you do division. But now we have a new tool that says, hey, to undo logging something base a half, you exponentiate it base 1/2, right? They're inverse operations of each other. Questions on that one? Okay, let's look at letter D. Is letter D a log equation? Yeah, I spy an equal sign. I also spy a log, so it's another log equation. Notice this time the unknown is the base. The unknown is the base. So log base some power of 25 is 2. What would you do to go about solving this one?
Like z to second equals 25.
Right, you can either do the around the world thing if you want. You could say z to the second power is 25. That gets you z squared equals 25. You could do that. Do the around the world thing. That's the conversion formula, right? That's why I gave it to you. If you know how to get from log format to exponential format, you're good. Oops, that should be 25. Or you could do what we just did. Does what we did still work? How do you unlog something base z? You exponentiate it base z, and you get something like this. What's z to the log base z of 25? 25, and you get 25 equals z squared. Either way works. Now, when you get z squared equals 25, let me flip that around. How would we go about solving for that? What's the algebraic technique? How do we undo squaring something? We square root it, and you have to remember, right? Y'all remember, when you take the square root of something, you have to consider both what? Plus or minus, all right? And what's the square root of 25? 5. Now, so we get z equals negative 5 or z equals positive 5. Those are the two solutions that come out of our algebraic process. But we always have to make sure that the answers that we get are either the ones that we want or the ones that actually work. Do they both work here?
Or no.
Only 5. Why? Why does negative 5 not work? Well, if the log were a negative, then it would be a fraction. But this is the base. This is the base. You also said no. Why'd you say no to negative 5? There's a different reason.
You can't square a negative number. Or no. That's wrong. Oh, it's because you can't log a negative number.
Do you remember when we had exponentials, what the legal bases were?
Yeah.
If you have log base b of x, your bases have to be a certain type because equals y, because this is the same thing as b to the y equals x. Your base has to either be between 0 and 1, in which case it's decay, or your base has to be greater than 1, in which case it's growth. So our base of logs are the same basis for exponential. We can't have a base of 1, we can't have a base of 0, and we can't have a negative base. They don't work. So why now does the negative 5 not work?
Because
It's less than 0. It's negative, right? So all you got to do is put an x through the 1, and then I know you've considered both of them. I want to see that you've considered both of them because I don't want to think that you got it just by dumb luck. Like you forgot to take the plus or minus, and so you only got the correct one that works. I want to see that you're considering both of them, and then you're judiciously casting out the one that doesn't work. You're thinking all the way through, right? You can't have a negative base. The base has to be between 0 and 1 or greater than 1, okay? Now, just to round this out, this takes us back to like what we had on example 1. This is another log equation, but it's solved for z already. So all we have to do is simplify the right-hand side to get it down to a single number. So let's see if we could do that. What I'm going to try and do, here's my strategy. My strategy is to write it as log base 5 of 5 to the something power. If I can write it as log base 5 of 5 to the something power, I know my answer is that something. Okay? That's using the inverse property. So let's go ahead and just come over here to the side. Let's go to the workbench. 5 over 125. I can simplify that, can't I? That's 1 over 25, which is the same as 1 over 5 squared, which is the same as 5 to what power? The negative 2th power. So I can write this as log base 5 of 5 to the negative 2th power, and lo and behold, then what is the value of z? It should be negative 2, right? Log base 5 of 5 to the blob is just the blob. Yeah, so whenever you have something like that and you're trying to simplify the expression, the easiest way to do it is just try to write your argument as a power of whatever the base is. And the power, or the exponent, is your answer, because that's what the log is, right? The log is the exponent. The log is the power. The power of logs. So that was an example of one of each of the 3 types. You either have a variable in the argument, in which case converting it to exponential is helpful. You either have a log in the base, in which case converting it to exponential is helpful, or it's already solved for z and you're just simplifying. So I think we could say this. This is kind of a summary. To solve a log equation, convert it to exponential, which means to exponentiate both sides. It's easier to solve in the exponential format. All right, how do you feel about logs so far? Feeling better about them? Getting used to them? No one was staying up last night unable to sleep because you were terrified of logs, right? You didn't want to go to sleep because they might show up in your dreams. Anyone dream of logs last night? No? I didn't either. All right. We talked about this in the opening. When you have your 2 inverse functions, b to the x and log base b to the x, in this case, the base is greater than 1 because they're both growth. They're going to be inverse graphs of each other, which means that they are reflections across the line y equals x. They're mirror images of each other. It's important to realize the features that switch places. The horizontal asymptote on the exponential graph becomes the vertical asymptote on the log graph, okay? And that's because a horizontal line, when you reflect it across the line y equals x, becomes a vertical line. And then what happens with the y-intercept on the exponential? The y-intercept is 0, 1. What happens to that y-intercept? It becomes an x-intercept of 1, 0. Remember, to find the equations of inverses, we interchange x and y. So we could do that point by point too. So 0, 1, if you flip it around, becomes 1, 0. All right. The domain of exponentials, what's the domain of exponentials? We'll use blue for exponentials. All real numbers. That must turn out to be the what of the logs? Not the domain, but the what? The range. All the x's become y's and all the y's become x's. So because the domain of exponentials is all real numbers, that becomes the range of your logs. Your logs have ranges of all real numbers. And what's the range of the exponentials? What's the range of the exponentials? Anything greater than 0. All y values greater than 0. Guess what the domain is of logs? Not y values, but all x values greater than 0. Yeah. So you see the parity there between the two? All the x information of one becomes y information of the other, and vice versa. Vice versa. Vice versa. Yeah. Okay. Now, we want to know how logarithmic growth functions compare to each other. We know that for exponential growth, there should be an x-axis here. It didn't really show up that well. So draw an x-axis in right there. we know that for exponential, the bigger the base, the faster the growth, right? 3 to the x grows faster than 2 to the x, 5 to the x grows faster than 3 to the x, so on and so forth. But is that true for logarithmic? Which one's growing the fastest of these four? We got log base 2, log base 3, log base 5, log base 10. Which one's growing the fastest? Log base 2, and which one's growing the slowest? Log base, that's actually 10. Yeah, it's 10. I know the image didn't transfer very well. So it's kind of the opposite of exponential, isn't it? We would say this: the bigger the base, the blanker the graph. The bigger the base, the steeper the graph, the less steep. Or you could say the smaller the base, the steeper the graph. It's the opposite, right? It's the opposite of the exponential. If you really, really want to slow down the growth, use a bigger base because you're taking the numbers in chunks of larger numbers. That makes sense. Instead of chunks of 3 for base 3, powers of 3, you can take chunks of 10, powers of 10. It slows down the growth a lot faster. Okay?
Like functions, or not functions, sorry, fractions. When you do the fractions, the bigger the number, right? It's like decay.
What's that?
Well, when you do like the fraction and the exponent.
You mean like 1/2 squared and 1/2 to the
Yeah.
fourth? Yeah, like exponential decay. Yeah, right. Now, speaking of decay, let's go ahead and let's draw one more picture over here. What if I have something of the form y equals log base b of x, but now the base is between 0 and 1? This is called logarithmic decay, or log decay, okay? So instead of just having log growth, we can have log decay. Now, what's going to stay the same? The things that stay the same are you still have a vertical asymptote at x equals 0, and you still have an x-intercept at 1, 0. That stays the same. But instead of growing, guess what it does? It decays, it decreases, it looks something like that. Okay? And if you wanted to, you could sketch an exponential decay function and reflect it across the line y equals x, and you'll get the logarithmic decay. All right? So we don't have to always have logarithmic growth. We can also have logarithmic decay if the base is between 0 and 1. Okay. Let's go ahead and sketch some of these dudes. Example 7. Sketch the following functions. Show the asymptote, the y-intercept, find the domain and range, and then determine any end behavior. Okay. F of x is -2 log base 3 of x plus 4. What's the parent function? Log base what? Yeah, so I'm going to come up to the side and say y equals log base 3 of x. That's your PF, your parent function. And do I know what that looks like? Do I know what I'm starting with? I do. It's logarithmic what? Growth or decay? It's growth. It's logarithmic growth because base is bigger than 1. So it's going to have a vertical asymptote at x equals 0. It's going to have an x-intercept of 1, 0. And it's going to look like this. It's going to look just like the natural log. Remember, we don't have to show the relative steepness unless we show more than one growth graph at a time on the same grid. Okay? So for all practical purposes, that's what every logarithmic growth function is going to look like when you start with it. Okay? It's just going to be increasing from left to right. Now, let's go through and think about what these transformations do, because I think it's in standard transformation form. In order, what are the transformations going to do? What does the negative out front do to this graph and any graph? X-axis reflection. Okay, let's go ahead and do the sequence as we go. If I reflect that across the x-axis, it's going to look something like this now, isn't it? It's going to turn it into logarithmic what? Decay. That turns it into logarithmic decay. So that's what I'm working with there. That's this one here. Okay, let's switch flavors here. I'll go to number 2. What does the 2 do to it? If it's multiplied out front? Vertical stretch by a factor of Or just 2. Yeah, vertical starts by factor 2. That's going to make the graph a little steeper. Do we typically show that on our graph? No, we just know that it's a little bit steeper. I'm not even going to show that, but it makes it a little bit steeper. Actually, I think I will show it. It makes it just a little bit steeper. It looks something like that. All right, and now we're down to the last one here. The last one is going to be this one. It's left 4, so you just put L4. Now, when I pick that graph up and move it left 4, it moves everything left 4. What's the most important feature that we always graph first that's going to move 4 units to the left? The vertical asymptote. It used to be at 0, and if I move it left 4 now, it's where? It's at -4. So we always draw our asymptotes first. And then the x-intercept, which was still at 1, 0, if I move that left 4 units, where does it end up at? It ends up at -3, 0. So I could draw it like that. And then all I have to do is come in here with my shape and draw it as a logarithmic decay function that's relatively steep. And there it is. I'll label it as f of x. I'll label it as f of x. All right, let's go ahead and answer the questions now. What is the domain of f?
From anything greater than negative.
Anything greater than -4. So the right way to write that is the set of all x such that x is greater than -4. That's set notation. Yeah, so it's important to track where the vertical asymptote goes because your domain is going to be either to the right of it, like in this case, or if we had reflected it across the y-axis, it could be to the left of the vertical asymptote. What's the range of this function? You can do that with your hands tied behind your back. All real numbers all day long. That's always going to be the range of your log graphs. Okay. What else does it say? Domain range. The y-intercept. Do we know the y-intercept? Let's find the y-intercept. How do we find the y-intercept for any function?
You set it equal to 0.
Set what equal to 0? X. So I'm going to say f of 0. F of 0. That's how you show me that you're plugging in a 0 for x. We get -2 log base 3 of 4. Log base 3 of 4 is about what? It's between which two integers?
0 and 1.
Not 0 and 1.
Or 1.
It's between 1 and 2, right? Because 3 to the first is 3, which is too small. 3 to the second is 9, which is too big. So log base 3 of 4 is 1 point something. 1 point something times -2 is -2 point something. Is that what we have on our graph? Is it some negative number? Yeah. So we're just going to leave it as -2 log base 3 of 4. That's the exact answer. What about the end behavior here? What about the limit as x goes to -infinity? Does that even make sense? Is there any left end behavior? No, I'm going to actually put none instead of D and E. The reason I'm going to put none is because the graph doesn't even exist there. So I probably wouldn't even ask you that on a test. There is no left end behavior. But what would be the limit as x goes to infinity? Hop on the graph and head out to the right, and where are the y values going? They're going down to -infinity. Are they going there very rapidly? No. Remember, this thing tapers off and flattens out really, really quickly. It almost looks like if you were to graph this on a calculator, it would almost look like there's a horizontal asymptote. But there is no horizontal asymptote. It just goes down to -infinity very, very, very slowly. Okay. All right. I think we'll stop right there for today. Any questions? Okay, cool. We should be able to finish this tomorrow. So we're looking at a Monday for a due date on your worksheet, and we'll also quiz on Monday. How's that sound? Sounds good. I agree. Okay. Clear your calculators before you turn them in.